Okay, so now we can finally move on to chapter 3. This is maybe the main content of the course, or where we're going to be doing most of our work. And we're going to, as the chapter is called, the name is factorizations in rings of integers. And what we're going to study is how ideals can be decomposed into products of prime ideals in this. And we're going to see how the uses of figuring this out. But to start with, the first thing we want to talk about is units in these rings of integers. And so this is the first section, so section 3.1, it's called units. And so, before you can talk about ideals and how they decompose, the first thing we need to do is talk about units, because, if you have a unit, it'll generate the trivial ideal, and somehow this is something that we need to be able to control. And what I'm going to do is I'm going to give you a structure theorem for what the units in a number field look like, in the ring of integers number field look like. And we won't prove it because the proof is somehow similar to the things that we'll see towards the end of the course, but it's somehow take us too far astray from what we need. But at least we'll be able to use this, the theorem and so on. So it'll be fine. So let me just give you some. Let's start with a nice proposition. So proposition 3.1.1 says the following. So let K be a number field. And I'm going to let, as usual, so OK cross denote the units in OK. So remember, unit means that it's an invertible element. So here, I think I want an element invertible under multiplication. So let me just put i.e. invertible element in the multiplicative group. Of OK. So yeah, OK is a ring. It has addition multiplication. Just forget the addition. Just think about the multiplication. Now I want things which have an inverse. Then what does the proposition say? Then it tells us that OK star is nothing but the set of elements alpha in OK such that the norm from K to Q of alpha equals plus or minus 1. So the units are going to be exactly the elements of norm 1. How do we prove this? Well, this isn't too hard because we know that the norm is multiplicative, so that's what we're going to use. So if alpha is a unit, then alpha inverse is in OK. Therefore, what do we have? We have the norm K to Q of alpha times the norm K to Q of alpha inverse. We know that norm is multiplicative, so we can write this as norm K to Q of alpha times alpha inverse, which is the same thing as the norm K to Q of 1, which is just 1. So what does this mean? It means that whatever this number is, it has an inverse. So because it's norm is multiplicative, let me just take out the minus 1 and put it there. So we have that the norm of K to Q of alpha is we know it's an integer, and we know that it's invertible. So it's an invertible integer, therefore the norm has to be plus or minus 1. Just because in the integers, the only multiplicative units are 1 and minus 1. So now let's do the converse. Now assume the norm of K to Q of alpha equals 1. Let's assume that we have an element of norm, well, okay, not 1, sorry, plus or minus 1. Then let's try and prove that this has to be a unit. The thing to note, remember, is we have a nice formula for the norm in terms of the embeddings. Assume this. I'm just going to let sigma I then be the embeddings of K into the complex numbers as usual. I'm going to just highlight that sigma 1 in this case is the identity embedding. then I can't remember what the name of the proposition was, but we knew that the norm from K to Q of alpha, same thing as the product over I of sigma I of alpha. And now, because I've said that the sigma 1 is the identity embedding, I've highlighted which one it is. I'm going to write this as alpha times the product I different from 1 of sigma I of alpha. And what I know is that this thing equals plus or minus 1, our assumption. This means that alpha inverse equals plus or minus this product, sigma I of alpha. But each of these sigma i's of alpha is again some algebraic integer. But each sigma I of alpha is again an algebraic integer. So alpha minus 1 is inside z bar intersect k, which is OK. So we're done. So it's again an element in the ring integers. So that completes this proof. So let's give a silly example. Let me just highlight that maybe. So we know the sigma, these embeddings might not send the number field to itself. It might send the number field to a different number field, like one that's completely real into one which has complex numbers or something. But what I'm highlighting here is that when I take the product over all of the embeddings, if you think of Galois theory, this product is invariant under all the Galois elements, and so this has to be an element of your original field. So, yeah, this holds because this product is over all the non-trivial embedding. Okay, so this is an example. KB Q square root 2. We know that Z root 2 is, well, so we know that the ring of integers is Z root 2. So, for example, is 1 plus root 2 a unit? Like if I give you a random number and you're trying to figure out if it's a unit in this, then it might be tough to try and find the inverse, but now we just need to figure out the norm. So now note that the norm from K to Q, 1 plus root 2, this is 1 plus root 2 times 1 minus root 2, which is just minus 1, so it's an inverse, so it's a unit. Great. So here's the main theorem about how the units in a number field look like. This is the main structure theorem. So this theorem is called Dirichlet's unit theorem. Let's get the number first. Theorem 3.1.3. So the reason I'm not going to prove this is, well, there's no known proof of this that just uses algebra. At some point, you need to do the analysis. You need to use logs or something. But you actually do have to use logs for this proof. And so it somehow takes us a bit astray from algebraic number theory, which is why I won't give the proof. But the theorem itself is useful. But if any of you can figure out a proof of this without using logs, well, then let me know. You'll be famous. So I'm going to let K be a number field. And here's some notation that you're going to set up for the future. I'm going to let mu k denote the set of roots of unity inside of k. So this is a set of x in k cross. K is a field, so I just mean non-zero x, such that x to the n equals 1 for some n in, well, the positive integers. So this is a set of all roots. If you think of it, this is a set of all roots of unity which live inside my field. So this is a set of roots of unity in K. I'm gonna, as usual, I'm gonna let R1 denote the number of real embeddings. R2 the number of complex conjugate embeddings. Complex conjugate embeddings, remember, in pairs, that we pair them up. Then what does the theorem say? Then it says that as a multiplicative group, the set of units in OK just is isomorphic to this group mu k times some number of copies of the integers, and the number of copies is R1 plus R2 minus 1. So sometimes there's some confusion about what this means. It doesn't mean that the units look like some root of unity times an integer. No, I'll explicitly somehow tell you what this isomorphism looks like. I'll explain what this is saying. So this is the theorem. Proof. We won't prove it. That's easy. So what is this saying? So let's make a remark. This theorem says that there exist let's see, R1 plus R2 minus 1 elements in OK star, call them, say, U1 all the way to UR1 plus R2 minus 1. There's these many units in here, such that for any V in OK star, we can write V equals, so it's going to be some root of unity to some power, so sigma I to the I, say, and then it's going to be this U1 to the A1 UR1 plus R2 minus 1 to the A R1 plus R2 minus 1. So every unit can be decomposed as a root of unity. So sigma, some element in UK. So every unit can be written as a root of unity times a specific choice of like a basis for a multiplicative set. So the isomorphism, OK star to mu k tensor say R1 plus R2 minus 1 is given by, you take your element V, you write it as zeta I times these units, and what do you send this to? Well, you send this to the first place you put your root of unity, and then you just put the exponents that you used, so A1 up to AR1 plus R2, and that's it. This is the isomorphism given. So I'm not saying that every unit looks like an integer times the root of unity. I'm saying that there exists a basis of units, and how many are there? There's R1 plus R2 minus 1 of them, such that every unit can be written as in terms of this basis, multiplicatively. Great. So this tells us essentially what the units look like. This is why it's called a structure theorem. And this has some nice consequences that we can actually study. So here's a corollary. Here's a 3.1.4. If k is, say, q square root minus d, with d in some positive integer square free, then OK star is just mu k, just a set of roots of unity. The proof, well, in this case, this is this field, because it's minus d and d is positive integer, this is completely imaginary. So this, in this case, R1 equals 0, R2 equals 1. Therefore, if you plug it in, you get a mu k And then you have an R1 plus R2 minus 1. So you have 0 plus 1 minus 1, which is 0. So you have no copies of Z there. So it's just mu k. In this case, R1. So the result follows. From the theorem. 3.1.3, I think. Great. And you can do an exercise if you want to, for when D is a positive integer, there'll be an exercise where you can figure out what all the roots of unity are inside of a field. So here's there's an exercise where you can finish it, and here's a more general corollary. 3.1.6. If I let k be q square root d, with d a positive square free integer, then the set of units just looks like plus or minus 1 cross z. So there is, in this case, there is a single unit somehow which generates everything. So I'm just going to highlight this. In this case, there is a unique unit. Unique unit u in OK star, which generates so OK cross modulo plus or minus 1. So it generates this. By quotienting out with plus or minus 1, I'm just saying it generates this copy of Z. Here I should put isomorphic, not equals. So which generates this thing, so that's isomorphic to Z. This unit you can arrange it so it has the following. One can make it so that this unit always has is always positive under the embeddings. So, and then say and under the standard embedding, so the identity embedding, so this is a real number because this is a real field. We have this unit is greater than or equal to 1, and this is called the fundamental unit. So there exists a single unit which will generate you this copy of Z. So every unit in here just looks like a plus or minus 1 times some power of this unit. And moreover, I can choose this unit so that under the identity embedding, this is going to be some real number, and I can make sure that this real number is always greater than 1. And then let's prove this. So in this case, so the previous exercise that you'd have done, in this case, say, let me just check, by exercise 3.1.5. Okay, we know about that. So we know that the roots of unity are just plus or minus 1. These are the only roots of unity that can live in this field. So the first part follows from theorem 3.1.3, with R1 equals 1, R2 equals R1 equals 2, and R2 equals 0. This is the case that we're in. So now I just need to check that I can always make sure that this unit that I have is positive, or is greater than or equal to 1. So now, if you consider what OK mod plus or minus 1 up to, essentially the set of units up to plus or minus 1. Oh, I just noticed a typo. That should be crosses. Yeah, great. So this is isomorphic to Z. So take any unit mapping to a generator of Z under this isomorphism. Call it U. Let's call it V. Then one of the following, if you have plus or minus V or plus or minus V inverse, these are all units. One of these is in the set it's in this interval from 1 to infinity. The real numbers, there's 4 choices. These are all real numbers, and in the inverse, you can check that one of them has to lie in this set. So and there's going to be only one. So let U be this unit, and then you're done. Okay, I'll remember to fix the typo in the notes. Great. So knowing about we know about what the structure of units are. This is going to be useful later on, like when we're solving Diophantine equations and so on, and when we're trying to study the factorization of ideals. But this also has some other uses for irreducible elements in this ring of integers. So here's proposition 3.1.7. As usual, okay, be a number field. And let, say, alpha be in. Okay. What does it say? If the norm from K to Q of alpha equals plus or minus P, with P a prime number, then alpha is an irreducible element in this ring. Alpha is an irreducible element in okay, so remember, irreducible element means that if I can factor it, one of the two things always has to be a unit. So proof, let alpha equals beta times gamma, say. Want to show one of beta or gamma is a unit. That's what it means for it to be reducible. So now just take norms, and you get norm from K to Q of alpha. This equals the norm from K to Q of beta times the norm from K to Q of gamma. And we know what this norm is. This is plus or minus P. Now, since P is prime, so P is a prime number, we must have the norm. We have one of these equaling, let's have this, or the norm K to Q of gamma equals plus or minus 1. One of the two things have to happen because we can't divide this prime. Remember, the norm is always just an integer. We must have one of those things, therefore, where is it, therefore? Thus, one of beta or gamma is a unit. And we're done. Cool. I should now give you a warning that the converse is false. Warning, the converse is false. For example, in Z square root minus 1, the element 3 has norm 9 but is irreducible. Okay, so this isn't an if and only if. Okay, so what does this tell us about elements in our field? Well, it tells us basically that all elements can be written as a product of irreducible elements. So here's a proposition. The thing is, it might not be unique. So proposition 3.1.9. K be a number field. And alpha some element of k, be non-zero, 0. Maybe I want alpha in OK. I think I want alpha OK. Be non-zero and not a unit. Then alpha can be written as a product of irreducible elements. So notice that I've not said the word uniquely. So you can't uniquely write it as a product of irreducible elements, but you can write it as a product of irreducible elements. So here's the proof. We do this by induction. On the size of the norm of the absolute value of the norm of your element. If the norm, k to q of alpha, equals 2, then by the previous result it's irreducible. Then it's reducible by, what was that called? Prop 3.1.7. 3.1.7. So now assume result is true for all beta such that the norm from k to q of beta, so the absolute value of this norm is less than the size of the norm of your element alpha. Oh no. So assume that the result is true for all beta with smaller norm. Then if alpha is irreducible, we're done. Then we can't write it as a product of irreducibles. Otherwise, alpha equals, say, beta times, well, I shouldn't use beta. Well, okay, I'm gonna use beta. Otherwise, you can decompose alpha into product of two things, and where you're gonna have, by the properties of norm, you're gonna have the norm, these two norms, of the norms of beta and alpha and gamma, are both going to be smaller than the norm of your element alpha, because they divide your element alpha. Therefore, by our assumption, we're assuming that the result holds. So we assume that for anything of smaller norm, that it can be written as a product of irreducible elements. So therefore, we can write beta and gamma as a product of irreducible elements, and so forth, and so can thus so can alpha, because you have beta as a product of irreducible elements. Change it for a product, and that change beta for the product of irreducible elements, change gamma for product of irreducible elements, and then you've written alpha as a product of irreducible elements. And we're done. So in this ring of integers, every element can be written as a product of irreducible elements. As I stressed before, the problem is that it's not unique. So here's a definition of what I mean by unique. So we say a ring has unique factorization. You might have seen this definition before. If whenever you have some product of the form P1 to Pn equals Q1 to Qm with say a ring R has unique factorization, if whenever you have a product of elements like this with the Pi's and Qi's irreducible elements in your ring, then you have not only does n equals m, so you have the same number of things on each side, but after relabeling, after relabeling, we can write, after changing some of the indices, we can write pi equals ui times qi with ui in a unit. So just like with the integers, every integer can be written as a pair of the prime numbers, uniquely up to a unit. So you can always put plus or minuses somewhere along the way, and this will change. But up to units, and this factorization is unique. So this is what we mean by a unique factorization. And what we're going to study is when do our rings of integers have unique factorization, and how do we somehow measure how far away a ring is from having unique factorization. Having unique factorization is great. When your rings have unique factorization, you can do amazing things. For example, like people thought that they could prove Fermat's last theorem at some point, and they thought they could prove this because they thought that all these rings of integers were always unique factorization domains. Turns out that's not the case, but in the case where it is a unique factorization domain, then you can actually prove this. But we don't know exactly how. There's lots of conjectures of how often are these rings of integers unique factorization domains. We don't actually know in general. So here's an example. And I'll finish with this for this. So an example, for example, z and z square root 2 have unique factorization. We'll see why z root 2 has unique factorization later on. But here's a non-example. If you look at z square root minus 10, for example, this does not have unique factorization. Why is this the case? Since you can write 2 times 5 equals 10, but this also equals minus the square root of minus 10 times the square root of minus 10. Okay, again, maybe I should be, here I have minus I, so I should write the square root of minus 10 as I times the square root of 10, so that I have a fixed choice of root of unity here. So if I write this, so here's two different factorizations, and I claim that 2, 5, and both of these, the square root of minus 10 and minus the square root of minus 10, these two elements here, this one and this one, are all irreducible elements. And we claim 2, 5, minus I root 10, and I root 10 are all irreducible. So how do we see that? Note that, let's look at their norms. The norm, let me call this element, this k, so I don't have to keep doing. The norm from k to q of 2 is just element 4. The norm from k to q of the number 5, this is 25. And the norm from k to q of I root 10, this is just 10. Now, if you think about what the norms of general elements in here look like, we've solved this in one of the exercises from one of the problem sheets. Every element of K has norm of the form x squared plus 10y squared. Pick a random element a plus b root 10, or a plus b minus root 10, and then you figure out what the norm is, and it's always going to look like this form, some x squared plus 10y squared. And note that this can't be plus or minus 2 or plus or minus 5. You can't have you can't find integers x and y such that x squared plus 10y squared equals 2 or 5. If you did, then imagine you did, and think of if you think mod 2 or mod 5, you'll end up with a contradiction. So what does this tell us? This means there can't be any irreducible elements dividing 2, 5, or I squared root of 10. Why is that? Because if I had an irreducible element dividing them, then when I take norms, then the norm of the thing that divides them would have to divide its norm. So I'd have to have an element whose norm divides 4, 25, or 10. The only numbers that divide 4, 25, or 10, the only non-trivial numbers that divide these are 2 and 5. But I said that there is, or plus or minus 2, plus or minus 5. There are no elements like this. So there are no elements that can divide 2, 5, and minus 10, well, square root of minus 10, so they're reducible. Okay, so this is indeed a factorization of the number 10 as two different things, and where everything is irreducible. Great. So in order to fix, as I think I've mentioned several times, in order to fix the fact that we don't have unique factorization, what we're going to do is we're going to not try and factor things into, we're going to try not to factor things into reducible elements, but we're going to factor things. We're going to take an element, look at the ideal it generates, and then factor that ideal into prime ideals, and then we will have unique factorization. Irreducible. Let me just put a remark. To fix this, we will use ideals instead. That's what we'll start moving towards next lecture. Okay, I'll leave it there for now.